All right, so today we're going to have a look at decidability and what it means to, well, be able to decide a proposition, as it were. So I'm going to start with the definition of decidability. And we've already seen it or like vaguely mentioned it last week. But the idea is that if you have a given set, you can declare what it means to have proofs that either this set is inhabited or it's not. And so it's an inductive definition where you can either have a proof of A, in which case A is indeed decidable, or you can have a proof that A does not hold, in which case it's also decidable. And because we only have these two constructors, we're explicitly stating that we can always know whether either A holds true or A can be disproven if we have a value of type decay. All right, so let's keep this in mind. And we're going to have a look at De Morgan's laws. So if you remember CS 106, maybe even 103 with the basic logic rules, you have this idea that conjunction, so and disjunction or are dual. When you take the negation of one, you get the other with the sub formulas negated. And that's just true when you're using Boolean logic, the logic underlying hardware circuits. And we'll see whether it's still true when you're looking through the constructive lens. So the difference between 103 is that in 103 you're just looking at logic in general, but here we're looking at programs that are actually computing evidence of statements. Yeah. So it's a bit of a refined idea around logic.
Yes. So De Morgan's laws are based on the observation that the assignment of 0 and 1 as false and true is completely arbitrary. And if you decided to do it the other way around, as I like to lie, the Australians do, then everything works just fine. All of your components still do sensible things. It's just that they do, things you weren't quite expecting.
Right, so the first one, we're starting with an easy one, I think. It's saying that if it's not true that A or B is true, then we can conclude that both A is not true and B is not true.
Yes.
Or can be disproven. I mean, it's not true anymore, as it were. That negation means not true in constructive logic. Yes. And I'm saying it's the easy one because I think Otto might be able to figure this one out. Oh, I guess Otto is crap these days.
Yeah.
So, I mean, let's k-split on it. We're going to get our assumption that not A or B. So I'm going to rename it A or B. Maybe with uppercase, actually, because I'm talking about the types. And then we need to prove both that not A and not B. Let's try Otto again. Maybe, no, still not. Okay. So we're proving a conjunction. There's a single constructor for it. It's the comma, so we can always use it. And now we have to prove two sub-goals. The fact that A does not hold and B does not hold. So if you do a bit of normalization, actually, or it's going to maybe show us the ugly encoding in the standard library. Oh, no, okay. So we need to prove that A implies false, assuming that A or B implies false. And so it's hopefully clear how we're going to proceed from here. We're going to say, well, you're claiming that A holds true, so you better give me an argument of type A. And now I need to prove that you were full of it. And luckily, I have in my assumption the proof that if I get to prove A or B, then I can conclude anything. So I'm going to use this assumption. Now I've reduced the problem to proving A or B. And I have a proof of A on my hands. It's very easy. Okay, finally,
The
Agda is
hardest bit
able
in the
to.
proof is figuring out how to type that Unicode subscript 1.
Yeah. um, right, and of course, for the other one, it's going to be exactly the same thing, except that this time around, we're going to get a proof of B, and we're going to inject it on the right-hand side instead of the left-hand sides. So I don't know what Agda is so bad at this. It's maybe too early today for Agda. Okay, let's add some params so that everything is aligned. And there we have it. But so if you look at it in terms of like information theoretical content, like we were looking at yesterday, right? You have a proof here of a negative statement. So you have 0 bits of information. The only thing you know is that you can discard impossible branches. And now you have a conjunction of 2 negative statements. So the conjunction is sort of adding the bits because you have values on each side. Is it adding or is it? Yes. And you have 0 on both sides anyway, so you're not getting any like bits of information out of that 0 bit input,
Yes,
which
that's
is
going
good.
on is pure refutation.
Yes. Do you want to do the other direction?
Fine. Okay. Don't know whether I can type this symbol.
Alt W. Yep.
Yeah. That's the trouble, is that I learned to use Emacs on a BT100 terminal. So that was before the invention of the Alt key.
Okay.
Okay. So I can see I've got a pair of proofs, one of which negates A and the other negates B. And I can expand that not A or B to A or B implies false and pull it over to the left-hand side. So if I load and I look at my goal, you'll see I've chosen vaguely sensible names for things. So we have separately the ability to get rid of A's and B's, and we're trying to get rid of A or B. We're going to make the devil pony up which of A or B they've chosen, and whichever they choose, we've got something we can whack it with. So here, in this case, they chose A, so we say na to A. And here we'll say nub to b. No problemo.
And yeah, again, we have the same idea, right? We started with no information whatsoever. Well, I mean, no bits, and we ending up with no bits. So far, so good.
Yes. I mean, we forced the devil to give us a bit. And then we were ready for whichever they chose.
All right, so let's see another one. So now we are looking at the idea that if you negate a conjunction, it's the same as the disjunction of the negation. So if you know that A and B does not hold, then you're able to tell that either A does not hold or B does not hold.
Yes.
And if
so
we
what
start...
this is saying is that if they're not both true, you know which one's false. And that is a bit of a stretch if you don't have the means to find out for your bits in your computer with your 0 volts and your 5 volts, your little voltmeter will tell you which one's false. You can find out. But if it's just an arbitrary bunch of arbitrary logical statements, logic can talk about some pretty weird stuff that you have no means to test. So you're in trouble.
Yeah, so here it's kind of tricky. If you look at the context, right, you have this proof of a negation, which is a function. The only thing it can do to a function is apply it. There's no way to inspect it. To go see inside whether this is saying that either A or B is wrong. Like, there's no way to actually look at the code of this function. So the only thing you can do is make progress on the goal, but here you have to make a choice already. You have to already know whether A is empty or B is empty. And because you're generic over A and B, this means that your answer should be valid no matter what A and B are. And so, of course, if you had such a proof, you could, as a user, sometimes call it with A being empty, sometimes call it with B being empty. So having a uniform behavior, no matter what A and B are, is not going to fly. So one way to fix this is to actually formulate that statement to be about, well, okay, we could be a bit more subtle here, but to be about decidable types. So we're saying, I need to get a bit of information from somewhere, and that somewhere is going to be an extra argument telling me whether A is inhabited or not. Or, I mean, in full generality, you could prove this.
If you can decide either of them.
Then you get to find the answer, but we can just do the decidable A version, and then by symmetry, I mean, you can see that A and B here are playing completely equivalent roles, right? Because you can always swap the two sides of a sum and the two sides of a product, so and get something equivalent. Right, so let's look at this new context now. I have this extra assumption telling me whether A is true or not. I can split on it. I can get either an A or not A. If I get an A, then I know that I won't be able to prove not A, because that would be absurd. So I'm going to jump directly to the second branch to prove not B. To prove not B, I get my hands on a B. And now everything is lined up properly. I know that it's not the case that both A and B are true, but I just got an A from the decision procedure, and I got a B from claiming that I was going to prove not B. So I can just call my thing, okay. It's really struggling with negation. Up. I can call my proof, and then what do I do to prove A cross B? I just pair the A I got my hands on and the B I got my hands on.
Yeah, it's important to remember that when you have a negated assumption, that's a kind of teleportation device. It allows you to say at any time, no matter what you're in the middle of doing, I'd rather prove A and B. So the problem with proving this without something like a decision for A is that whichever you choose, left or right, you get handed an A but not a B, or a B but not an A, and your escape hatch is no use to you. Whereas once we got handed this A, then all we needed to find was a way to get a B from somewhere, and we were home.
Yeah, so that's when Connor says teleportation, that's what we saw last week, right, with the principle of explosion. So here we're only proving bottom as the goal anyways, but no matter what the goal were, if you have a negated statement in your assumptions, through the principle of explosion, you can say, I'd rather prove the negation. All right, and if A is not true, well, we have a proof of not A, and one of the goals is not A, so we don't need to do any more work than that. We can just go immediately to the left and then return not A. All right. And then the other direction.
Yes.
If you wanna
so this is another
jump
one
in.
where don't know why I spent the effort on giving that a name. Right, if I load, look in the go, right, the devil is, we're going to force the devil to choose which one's false. But in fact, you can see we know they're both true. So let's, right, if I split that mechanically, Agda will choose names I don't like.
Mm-hmm.
So I'm going to do that by hand. Okay. And then we get, so we've got an A, we've got a B, and now we're asking the devil, make your mind up, love. And in one case, the devil gives us nah. So you can see here, we've got a refutation of A and an A. Here, a refutation of B and a B. So there we go.
Yeah.
3 out of 4 ain't bad. But you see, only one of them is magicking bits into existence. The other ones are either not involving bits at all or are extracted. We're being given bits rather than being asked to deliver them.
In a sense, this last one is weakening our assumption, right? We have a very strong assumption telling us exactly which of A or B is uninhabited, and we're jumping to, well, it could be either of them.
Yes.
Or rather, it's both of them are not inhabited. All right. So far, we've seen decidability more as a way to like recover some extra principles, but it would be utterly useless if we couldn't actually build any proofs of decidability. Luckily for us, it is of course possible. So the first one that we mentioned last week actually, but we didn't look at, is the decidability of equality on natural numbers. So just by the same reasoning principle that we had here, saying that because it has to be for arbitrary A and B's, if we don't have deck A, then making a choice, a uniform choice, would just not work. You couldn't decide in full generality the equality between two values of type A, right? Because here you would need to make a decision without being able to inspect anything, because everything is fully generic, on whether you're saying yes or no. And of course, if you're picking yes, we're able to find two values that are not equal to each other, like 0 and 1. So that wouldn't work. But if you're saying no, we're able to find two values that are equal to each other. It's even easier. We could pick any type that has an inhabit, or even an antitype, actually, like any type. Because by REFL, it's always true that a value is equal to itself. So there's no hope to get that generic thing. But for specific types, oh no.
Exciting letter N.
For specific types, we are able to explain to ACTA how to compute evidence that two values are either equal or distinct. So I'm going to bring both of them into scope. And then, well, here there's not very much we can do apart from looking at the values of M and N. And that makes sense, right? If you want to decide whether they're equal, you better start inspecting them. So we're going to proceed by induction on the first element. The idea being that, well, for 0, it's going to be easy. We know that only 0 is equal to itself. But if you know that something is non-zero, you're only getting slightly smaller numbers. So you need to, again, compare them against each other. Which is why you need induction. That's principle that allows you to define a symbol in terms of itself. Okay, so when is it the case that 0 is equal to n? Well, I'm going to look at n, and 0 is equal to itself, so that should be fine. And then if I have someone asking me whether 0 is equal to a successor of something, I'm going to say no. And then they're going to ask me, as per the definition of decidability, to build that function from 0 equals successor to the empty type. And as we saw last week, this is easily seen as impossible by ACTA. Because
one thing to notice, just of the way ACTA has punctuated this, if the last argument in an application is a lambda function, you don't need to put parentheses around it. This may look weird,
but it might be helpful. Yeah.
Sometimes it's useful to exploit that.
Or you could build it. So if you remember, last time we built one by saying, I'm going to build a proposition that distinguishes 0 from 1 by saying 0 is sent to true, 1 is sent to false. And then if I have a proof that 0 is equal to 1, I can transport a proof of true to a proof of false, which leads me to some kind of issues. All right, so now we have the other case. So that was the base case. Let's see, base case. And now it's the inductive case. So I am asked to prove that I can decide whether the successor of M is equal to N, and I get to decide whether M, the predecessor, is equal to anything I want. I can ask these questions because M is smaller, which means that it's a valid definition. So I can look at N first, because if N is 0, then once again, I'm asked to compare successor to a 0. These are two distinct constructors. I know I can tell them apart, so I can just dismiss this impossible assumption. And now we're in the tricky case. So I need to decide whether the successor of M is equal to the successor of N. And of course, that is true if and only if. Yeah. So we are going to perform the recursive call, then call the induction hypothesis.
Have we seen with yet?
No, I don't think so. I think so, yeah. Because I've been using let so far. But
yeah, but here we're interested in star. Okay. So what we're saying here, what this with thing is allowing you to do is to collect some extra information and bring it over to the left-hand side where we can do matching. So the point is, rather than using a case expression, which you might have used in Haskell, because there's still quite a lot going on in terms of pattern matching, and we might want to learn more about M and N as well as the result of this thing. It's useful to be able to do an auxiliary computation and get its result and stay left programming. And that's the crucial thing that that with allows you to stay on the left, do more pattern matching and all of that kind of business. It's I mean, I'd say it's useful, but that would count as boasting. I invented it.
So I think if I case split on this without saying anything, oh, okay, it's a bit. So these this ellipsis here, 3 dots, is actually standing for just repeat the previous left-hand side.
Yeah, actually.
So equivalently, you could write this, right?
Right.
So you're saying, now I'm defining an auxiliary function. I just don't give it a name because I don't care. I only care about throwing in this extra result.
Yeah.
So equivalently,
So you've
you
got
could
this vertical bar, which just separates the inputs we started with from the extra columns of useful information we've added to our match.
So what it does under the hood is something like this. You can see that here, I want to have the extra assumption that M is equal to N, well, that I can decide whether M is equal to N. So I could define this auxiliary thing here, and that would just work. The thing is that, okay, so here it's not too bad because the types are kind of small, but you can imagine as the types are getting bigger, if you need to declare the type, figure out where to insert the arguments so that the dependencies are respected and so on, it's going to be really painful really quickly. So instead you can use that gadget that does all of that magic for you. Oh, I had it in my kill ring. I shouldn't have retyped everything. And it's just equivalent. Under the hood, you're just saying, I have a function I'm not going to name that has this extra argument here. And then it shows up after the pipe telling you this is the separation between the ambient function and the next one in. And of course, this can be nested arbitrarily, right? You could add more assumptions here, and then you would get more patterns here. Anyways, in this instance, we're only getting a single induction hypothesis here that's telling us we know how to decide whether m is equal to n. So let's look at it. It's going to tell us whether we're in the yes branch or the no branch. So let's see. Well, let's not name them actually. Yeah. We don't care. So if we're in the yes branch, we got our hands on a proof that m is equal to n. So we could inspect it, for instance. And by splitting on it, Agda is like, well, the only way we could have built to prove that m is equal to n is if like m was literally n, or n was literally m in that instance.
So yeah, this is a fine example of using dependent types deliberately. You know, we looked at this piece of information and we learned something about this one. Remember, dot means I'm not asking you, I'm telling you. So because this is REFL, these two have to be exactly identical. And this is why width exists, because there's still indirect impacts of pattern matching on the result of the width showing up in the patterns for everything else.
Yeah, and crucially, the dot shows up here on the variable, because if you remember, this suck, we actually had to look at the argument to know whether it was 0 or successor. So this is not forced. This is us looking at it and deciding what the head constructor is. But then for the subterm, if we know they're equal by induction, we don't even need to look at it. And so now even Agda is able to realize that we're in the yes branch and everything is fine and dandy. And in the no branch, we know that m is not equal to n. So I mean, we're probably not going to be able to prove that successor of m is equal to successor of n. And now we need to go from here to there. So if we look at the types, if I can look at it, we need to take a proof that m is equal to n to a proof that m is equal to n. So if we're saying Sn equal Sn, and then I'm going to use the fact that m is not equal to n. If I can put it in. And then we need to go from here to there. So there are various strategies. One of them is to do this, which is not super elegant. So what happened here? Let me rewind. So if you remember, we had this proof that successor of m is equal to successor of n. Lambda where is an anonymous lambda function that allows you to pattern match. So here I'm saying the evidence that successor of m is equal to successor of n was arrived to by using REFL. And so under the hood, that means that they're actually equal. Well, they both start with successors, so we can pop these constructors. And then we have two variables, and these are only equal when one is literally the other. So it performed the substitution under the hood implicitly, and now I can use REFL here. But I think there's a bit too much magic in there. It's hiding what's happening a little bit. So I like to write this instead. If I have the right things in scope, I hope I do. Yeah, I do, actually. So, okay, let's look at the whole rather than saying it and then explaining it. So we're almost there if only we could remove a successor at the front. And one reasoning principle we know for equality is congruence. If two values are equal, then applying the same function to both values will yield the same results. So if only we had a function that would peel off a successor at the front, by applying it to both sides, we could get, through computation, an equality that m is equal to n. And if we look in the standard library, but we could have defined it ourselves. Okay, this is a terrible definition, of course, so let's not look at the standard library. But we have the predecessor function, which is exactly taking you 1 before the current natural number. So if you had 0, you can't go below 0, so you're just returning 0. But if you have the successor of something, you're going to return the predecessor. And it is exactly the behavior that we need here. So I can do this. And it will work because it will pop the constructor on both sides. And then, of course, we can start golfing this. So if you know composition, you can... there we go. So we're just grabbing the argument only to pass it to a function, to pass it to something else. You can just do this instead. Okay? That's good. All right, so far we've looked at decidability for arbitrary propositions, allowing us to recover some classical principles. And then most of the proofs, if not all of the proofs that we've done, have been about equality. But of course, there are more interesting predicates or relations than just equality. And turns out you can just define whatever you want. Do you want to define odd and even? Whichever way you want.
Goodness me.
There are choices.
There are lots of choices.
I think they should be mutual, but...
maybe. So why do we have we got Booleans knocking around?
Ooh, I see. Okay. We can have them if you want. Let's see. We're going to be here.
Although we could just define them. So I was going to use a trick for doing mutual definition without mutual definition.
Oh, I see.
Do you want to do it? I mean,
sure.
Yeah. Okay. See if I can do this. So let's see. I'm going to define what it is for a given for a number to have a particular parity. \bn.
Yes.
And I'm not going to be too clever about it. So I'm going to start by saying that even 0 has type. So parity false, right? So we're thinking of false as 0. 0 is even. So we want to make sure that what we're saying is exactly when the bit is as even or odd as the number, right? So I'm going to say, what is it, 0 spelled Z-E-R-O today? Okay, so got off the ground, right? That 0 has even parity. Okay, and then I'm going to define odd successor. So this is, and I've got number variables. So I'm going to say that if I know n has even parity, then I'm going to say that the successor of n has odd parity. And the other way around. If I know that n has odd parity, then I know that the successor of n has, once again, even parity. And now I can define even and odd in even is parity false and odd is parity true. Right. So I could have defined two separate predicates by mutual recursion.
And this is in fact what you have in the archives if you look at last year's lecture notes, if you want to see how it's done.
But this is a trick where you can turn a collection of mutually defined things into one thing with an extra index that tells you which branch of the mutual thing you're in, and it's sometimes useful to be able to compute with which branch you're in. I could have done something gnarly involving using not to avoid having two successor operations, but I really just thought if I was writing down separately the definitions of even and odd, this is what I would end up with. So yeah,
Yeah.
Is that something you can get on
Work
board
with, sure. And so here we have two definitions that are declared on the same line. And if you just use multiple names in a row, you're able to say all of them have this type instead of repeating the declaration multiple times. So I wanted to go through some examples. Let's see if we can prove that, let's be careful here. Yeah. 6 is even, and yeah, that works. 6 is even because 5 is odds, and 4 is even, 3 is odds, 2 is even, 1 is odds, and 0 is even. We're done. And of course, we can prove that 1 is odd. 1 is odds because 0 is even. Okay? So now what we would like to do is prove that we can decide whether something is even or not. So that seems like a sensible definition. For any n, we can tell whether n is even or not. So let's look at it. Well, you should expect this by now. The only thing we can do, we're not going to say yes or no immediately, is to look at n, so perform an induction. If n is 0, it should be easy. It's already even. And otherwise, we need to decide whether the successor of n is even. And I mean, so one way to do it is to look some more at n. If n is 1, then we know, okay, do we? That it's not even.
Yes.
Come on.
What's it?
What? Is that not? Huh? Oh no, it's even s.
Yeah,
Yeah, silly me. Okay.
So you have to
Can I-
stare at
yeah,
it quite
yeah.
hard to see why it's nonsense.
Yeah. So as before, I've used the anonymous pattern matching lambda, and I'm saying, well, if 1 is even, because it starts with a successor, that was proven using the even successor constructor, which is now telling me that 0 is odd. And this can be dismissed easily because if we look back up, the constructors for this family, they're only, you can only target the odd parity, which is true here in the conclusion, if you are successor headed. Right? True is the only one, but 0 is not a successor, therefore this constructor couldn't be used as for, therefore you couldn't have built a proof here, actually, that this is true. Okay. And now I need to decide whether it's true that successor of n is even. Well, I can use a with telling me whether n is even. So that gives me my induction hypothesis. And here you can see that it's a bit strange, right? Because when you're doing a proof by induction, you're only allowed to peel off one constructor. So here we're doing something slightly different. It's a stronger form of induction. So we didn't mention it in the very first lectures. Agda is a termination checker, making sure that the definitions make sense, and that gives you this extra power, right? So here n is clearly strictly smaller than successor of n because it shows up inside that term under some constructors. So we've made some progress towards 0 by peeling off a bunch of successors. Therefore, this definition is valid, but it's not quite just induction anymore. It's just the standard induction anymore. Anyways, we got our hands on the induction hypothesis, so we can look at it. And if n is even, then the successor of n will also be even. Agda finds that proof easily. And if it's not, then it cannot be the case that the successor of the successor is even. Why is that? Well, same as argument as for 1, right? It's only even as the successor of the successor if the successor itself is odd, which means we got this proof by using the odd successor, which means that now we have a proof that even, not even, no, what?
You'll have something that you can refute using n.
Even n, that's a proof of even n, yes. Okay. And this is a proof of no even n. And of course, now that I've inverted the construction to say, well, the only way I could have come here is through these constructors, I get to come here. And then you could do the same thing for odds, right? But I don't know about you, this seems a bit nasty to me. So maybe there's a better construction to do. And of course, the trick is to notice that we're defining even and odds mutually. So it would only make sense to decide them mutually too. So I can define these things.
Yes. And what of course you could say is that you can decide.
Well, we still have time.
Yeah.
So I'm going to roll back and say, well, let's not look at the successor of stuff and so on. Instead, if we, let's stop jumping around. When is it the case that even of soc n is true? Well, precisely when the n is odd itself. So instead of deciding whether the double predecessor is even, I'm going to decide whether the single predecessor is odd. And if it's odd, odd n. And if it's not odd, not n. There we go. Nicely aligned. And of course, if the predecessor is odd, by flipping the polarity using the even s, we're getting there. And if it's not, we still have to do a bit of inversion, but it's only one layer. because we're going down only by one constructor. Then, Norden. Okay. And Norden now has a fairly similar behavior, so I'm going to prove it by induction over n. If it's 0, well, even I can figure out that 0 is not odds. And then if it's successor, well, it's only odd if the predecessor was even, so I can look at this thing instead. And yes, even n, or not, no, even n. Yes. This goes through, actually. And here, again, I need to invert that assumption by saying I got to it by using the odds constructor. Oops. And now I can dismiss that branch entirely. So now for any number, we can decide whether it is even or odd. So I might be able to prove that even of, I don't know, 10 is yes of something. There we go. So just by computation, instead of building these disgusting proofs where you have one constructor every time you go under a successor, you can just use this decision procedure, because you've proven that you can always know whether it's true or not. And as Connor was hinting at earlier, this is maybe not the best proof yet, right? What would be a more useful statement than just saying, I get to decide whether something is odd, I get to decide whether something is even?
Maybe we might not want to talk about just a decision problem. We might want to say we can test any parity, right? These two are special cases of testing whether parity false or whether parity true. We should be able to test parity B for any n. So that would get us the same thing cooked differently, paying attention to the coincidence.
Yes.
But it's also the case we definitely want to know that, you know, if we find out, I mean, it would be a terrible shame if there were numbers knocking around that were either both even and odd,
or neither.
Or neither. That would be a nuisance.
So in a sense, this is showing that the notion of decidability that we have here is really useful, but it's also somewhat limited, right? Because we're saying either you have A or you have something that doesn't give you any information except the fact that you have the ability to dismiss any claims that A. But when you're looking at even and odds, you don't really care that you're not even. What you would like to have is actual, like, constructive, like, inductive proof that you're odds if you're not even. So a more principled decision procedure would be to say, well, not only can I decide which one you are, well, not decide, but like I can produce a Boolean that will tell you what the parity of the number is. So instead of saying, for any Boolean, I can tell you whether you are of this parity, you could say, I can compute a Boolean telling you what parity you are. So that would be something like this, parity. So it's taking a natural number and it's returning, so with in sigma, but not too much. Oh, better call them the same thing, otherwise it's very tricky to prove. Oh, it's not in scope.
Yeah.
Oops. Some base product here. Or rather, oh no, maybe I can, yeah, this thing. Let's do this thing. It's all equivalence. So seeing it from the proof point of view, for any m, I can prove that there exists a Boolean which tells me what the parity of m is. And now this function, if you look at the definition of there exists under the hood, it's actually just sigma. If you look at the definition of sigma, it's the one we saw a while ago. It's a pair of first a value for the first type, and then the proof that that value first satisfies the predicate b that you're giving as the second argument. So if you roll it back to our example, so this is saying if you give me an m, not only will I compute a Boolean, but I will also compute the proof that it is the parity of m. And of course, from that, you can recover that even and odd are decidable, because you're looking at just looking at the Boolean and seeing whether it's telling, yeah, it's true, or no, it's not true, that it is even. And I think we've run out of time, but this is a good exercise if you want to try to prove this.